In this video, I'm going to be deriving an expression that shows the relationship between temperature and pressure for an ideal gas in an adiabatic reversible process. So first we're going to start out here with the first law of thermodynamics. Here du is the change in internal energy, and that equals the change in heat minus the pressure times the change in volume. And we also have here a pocket of gas. We're going to call that pocket 1, and then as it rises in altitude, we have a second pocket here, pocket 2, which is, as you can see, much larger than pocket 1. So in just doing some definitions here, because our process is reversible, we can say that our pressure inside our pocket of gas is equal to the pressure outside of our pocket of gas. So in this equation, our pressure here is the external pressure. But because they're both equal, we can say that our pressure inside is equal to our external pressure, and so we'll just continue to write this as P. And next, the word adiabatic can be defined as a process with no external heat applied. So we can say that the change in heat is going to be 0. And lastly, because we are applying this for an ideal gas, we can say that the change in internal energy is equal to the specific heat times the change in temperature. And we can also say that our pressure P is going to be equal to the ideal gas constant times temperature over volume. So applying all of these things to our equation, we can rewrite this as the specific heat times the change in temperature is equal to negative gas constant times temperature over our volume times the change in volume. Now we're going to move T to the other side, and we can rewrite this as now CV times dt over T is equal to negative R times dV over V. And so now we're just going to integrate. Before we can do that, we need to figure out what our limits of integration are. And as we mentioned before with our pockets of air, we said that they each have an internal pressure and an external pressure. Well, because they have pressures, they also will have a temperature and a volume. And so those are going to be our limits of integration. So we can write this down here as our limits of integration are T1, T2, and over here, V1 to V2. Solving this out, it's going to give us CV times the natural log of T2 over T1, and that is equal to negative R times the natural log of V2 over V1. Working on our equation a little bit, moving the CV to the other side and getting rid of our natural log, we can rewrite our equation here as T2 over T1 is equal to V2 over V1 to the negative R over CV power. Now, talking about our ideal gas law again, we can also say that volume is going to be equal to the gas constant times temperature over pressure. Applying that back into our equation, we have T2 over T1 is equal to R times T2 over P2 multiplied by, since the V1 is on the bottom, we're just going to flip this equation and we're going to have P1 over R times T1, and this is all to the negative R over CV power. As you can see here, the R's are going to cancel out, and that will give us T2 times P1 over T1 times P2 to the R over CV power. Now next what we're going to do is we're going to take this T2 over P1 and we're going to move it to the other side. And by doing that, we'll have to add exponents. So that's going to give us T2 over T1 to the 1 plus R over CV power. And that's equal to P1 over P2 to the negative R over CV power. Now we're going to take this power over here and we're going to find a common denominator, so we can rewrite this as CV plus R over CV. Now we're going to take this power and we're going to get rid of it, moving it over to the other side. And so in order to do that, we're going to have to multiply by the reciprocal. And so by multiplying by the reciprocal on the left side of the equation, that just cancels this out. And then on the right side of the equation, that'll give us CV over CV plus R. These two are going to cancel out. And so finally, we can rewrite our equation as T2 over T1 is equal to P1 over P2 to the negative R over CV plus R power. And that right there is our expression relating temperature and pressure for an ideal gas and an adiabatic process. That's all I have for you today, and thank you for watching.